This lesson deals with supplemental problem 412. You can find this problem in the ECE302 ebook in the Chapter 4 supplemental problems starting on page 19. In this supplemental problem, we're going to take a look at inductive switching without using a damping diode. Go back to the BJT switching circuit we had in Chapter 3 on page 45, and let's replace the BJT with a power N-channel MOSFET, in particular an IRF 530. Search for the Vichy IRF 530 datasheet and construct a SPICE model at a gate source voltage of 5 if we assume that the threshold voltage is 3 volts. An alternative to a damping diode is to use a Zener diode as a clamp as shown below. Here's our switching circuit that we had in Chapter 3 with the BJT replaced by a MOSFET. And now we're going to put a Zener diode here that's going to act like a clamp. This was taken from a magazine article in Modern Electronics in volume 17, number 9, on pages 54 to 60, and the article is entitled The Power MOSFET. This was written by Forrest Mims. It turns out that the IRF 530 actually has a Zener diode built into it. And this is the diode between the bulk and the drain, and by introducing impurities, you can make this diode that's here break down at a lower voltage, in this case around 100 volts. Well, let's add this to our SPICE model that we did in number 1, and let's plot the same results we did in Chapter 3 on pages 48 to 49. Then, can you explain why the Zener diode circuit's switching much faster than the damping diode circuit of Chapter 3? I found the datasheet for the IRF 530 on Vichy's website, and let's take a look at what that datasheet looks like. Every datasheet is a little bit different. There are some similarities between datasheets, and usually on the first page, I'll show the part and sometimes pin out, and then some of the features of that particular part. Generally, are always positive statements, and a description of how you might use that. Here's a product summary about some of the highlights of this particular part, and then usually on this first page, there's absolute maximum ratings. You can see here that the drain source voltage has a maximum of 100 volts, and that's really that Zener diode that's built into the MOSFET. And the next page has table data about the FET in what's called static and dynamic. Static is DC, dynamic is AC. We'll take a look at AC results coming up in Chapter 5. And then the next page are characteristic curves, and find figure 1, and then to model this particular transistor for a gate source voltage of 5 volts. Now the steps here are half volt steps, so here's 4.5 volts, here's 5 volts. This is a log scale and this is a log scale, so it looks a little bit different than what we were doing in our class notes. It lets you see these curves in a little more detail. We're in current saturation here with a gate source of 5 volts. That's right over here on this particular point. Here is 1 amp, and here's 2 amps, and here's 3 amps as you go all the way up to 10 amps. For a gate source voltage of 5 volts, the leveling value of this current occurs at 3 amps. Let's go back to our notes, and that's where I got this from. From Chapter 4, page 13, we had the value of K was I sub D when it's in saturation over the gate source minus the threshold quantity squared. This was 3 amps. The gate source voltage was 5. The threshold, we were told to assume a value of 3, and let me show you why I did that. Go back to this table on the previous page for the static curves. Here's our threshold voltage, and minimally it's 2 and maximum it's 4. So I took the average of those two, which would be at 3 for the typical case. Solving this, you get 750 milliamps per volt squared. Next, we're going to write our SPICE file. We'll need to number the nodes. I'll call this 1, 2, 3, 4, and 5. Need a title. I said inductive load, and then I need another line here. I wrote down with a Zener clamping diode, and then put an asterisk. Whenever SPICE sees an asterisk, it just ignores that line. This is the same file we had in Chapter 3, except that I made some minor changes to it. The value here was 40 microseconds. I wound up making this number 40 nanoseconds. And likewise over here, this was 40 microseconds in our Chapter 3 simulation, and I'm going to make that now 40 nanoseconds. I had to play with this because this is going to switch really fast. And the rest of the circuit's the same except for the MOSFETs now between 5, 2, and 0. 5, 2, and 0. Then I have to give a fourth terminal, which is the bulk connection, which is also tied to 0. And then my model for the IRF 530 is going to be an NMOS transistor with a threshold voltage of 3, and then the value of Kp is twice the value of K. You had 750 milliamps per volt squared. You double that, you get 1.5. We have to add the Zener diode. It's not part of the MOSFET modeling. And when you do that, this is what's called macro modeling. It's allowing you to add some more detail. Put a Zener diode in. between 0 and 5. I'm going to just give the value of the breakdown voltage at 100 volts. We're going to operate the Zener diode in the Zener region. When I ran the simulation, I had convergence problems. And what the SPICE program does is it takes a number of iterations during transient analysis, and if it can't find an answer, it quits. This goes back to the early days of computing, when computing wasn't for free. You had to pay for it per second. They built in essentially a safeguard to prevent burning up all of your account money. This is defaulted to 10 iterations. So whenever it's solving for a voltage or a current, if it can't find the answer in 10 iterations, it just quits. ITL4 is taking that number and increasing it. I played with this, but I made it 100, and when I did, I was able to get convergence in this simulation. Let's take a look at node voltage 1 to see if it is a square wave of 0 to 5 volts. Take a look at the output voltage here, and then the current in the drain of the transistor, and then we'll take a look at the current in the Zener diode going in this direction. That's on the next page. So you can see here I've got a nice square wave of 5 volts. This is also the gate source voltage, and this is high, this is low, and it's pretty much close to being 0 volts. We'll calculate this in a little bit. And then when I did the switching, there was a shooting up of voltage and stopped at about 100 volts, and then went back down to 5 volts when the input was back at 0. And then the current in the drain of the transistor starts out at 0 and starts to increase and reaches 28.434 milliamps when I do the switching. And the current in the Zener diode, basically 0, and then it shoots up to about the same value, 28.421 milliamps, and then shoots down to almost 0 in a very short amount of time, 0.0175 milliseconds from the instant that this started. When t is between 0 and 2 milliseconds, our input voltage is basically 5 volts, and we've driven M1 into the ohmic region. We have a resistive voltage divider in steady state. Let's calculate the resistance of the drain to source when we're operating in ohmic. Now I'm going to go back to chapter 4, page 23. We had a formula for a JFET where this was the pinch-off voltage. So I replaced the pinch-off voltage by the threshold voltage, because the equations are basically the same. Value of K was 750 milliamps per volt squared. Gate source is 5 volts, and our threshold was 3 volts. We get pretty small resistance, 0.333 ohms. The inductor is a short circuit in steady state, so what we've got for drain source voltage, which is also node voltage 5, is 5 volts voltage divided with the resistance of the MOSFET with the series resistance of our circuit. This is a little bit less than 10 millivolts. It's 9.496 millivolts. In the SPICE simulation on the previous page, we saw that we had 9.4393 millivolts, basically the same number. The current in the inductor in steady state is going to be the voltage across the resistor of 175 ohms, and that's going to be 5 volts minus the drop across the drain source. The inductor is a short circuit. The difference of those two node voltages, that's 28.52 milliamps. In our simulation, we saw that the current in steady state was about 28.434 milliamps. Now at t equals 2 milliseconds, we switch from an input of 5 volts to 0. We cut off the transistor. It becomes an open circuit. But we had a current flowing in here just before that happened of 28.52 milliamps. And that current must still be there. And that current now has no place to go except into the Zener diode, and then invokes the Zener voltage of about 100 volts. We'll see 100 volts across there. In our simulation, we saw 100.503. Let's next calculate the current that's in the inductor, which is also the current in the Zener diode. Back this up over here a little bit. When current's flowing, this is 100 volts. And you can treat this like a battery. The current that's flowing in here is some first-order differential equation like we had seen in ECE302msu. It's going to be some A plus B times e to the minus the quantity t minus 2 milliseconds over tau. Tau is L over R equivalent. We need to find the resistance seen by the inductor with all the independent sources set equal to 0, shorting this back to ground, and this battery effectively shorting that back to ground. And looking in these terminals, I see 175 ohms back to ground, back to this terminal of the inductor. R equivalent is 175 ohms, and that gives me a time constant of 343 microseconds. Current that was in the inductor prior to this changing of the input from 5 volts to 0 was 28.52 milliamps. And that must still be the value as we cross 2 milliseconds. Evaluating this equation at 2 milliseconds plus, we're going to get e to the 0. E to the 0 is 1. We just get a plus b is equal to this 28.52. If you wait long enough, the inductor will become a short circuit, and the current that flows in here would be the voltage across this resistor divided by the resistance. It would be 5 volts. This is a short, so minus 100 divided by the resistance of 175, and you get a negative 542.9 milliamps. That's actually not going to happen because as the current begins to decrease in here, eventually the zener is going to shut off. But what's interesting is the differential equation doesn't know that, and it's going to follow this until something switches or changes. We can solve this equation even though part of it's never going to happen to get the numbers that we need to be able to solve for that point where it does shut off. That A plus B is equal to this. We can solve for B by bringing A on this side of the equation, minus A, and A was a minus 542.9 milliamps, so it becomes a plus 542.9 milliamps. Adding these two together, I get 571.42 milliamps. Current that's in the inductor, which is also the current in the zener, is going to be A, which is minus 542.9, plus B, 571.42 milli, multiplied by e to the minus quantity t minus 2 milliseconds over 343 microseconds. As I just mentioned, the zener will shut off when the current through it passes through 0. The current that's in the inductor is the current that's in the zener. Suppose that it passes through 0 at some time t1. Just put in for t1, solve for t1. Bring this on the other side of the equation. We've got this expression over here. I'm going to divide this over here and then bring this over here, taking the reciprocal and making this a plus sign. Make the algebra a little bit easier. The ratio of this to this is 1.0525. Take the natural log of both sides of the equation. The natural log of E is just the argument, which is T1 minus 2 milli over 343 micro. Natural log of 1.0525. Then multiplying by this number, I've got 343 micro times this log, which is 51.2 milli, and then bring the 2 milli on the other side of the equation. Time T1, time it takes the current in the zener diode to pass through 0, is 2.01756 milliseconds. Well, that's 2 milliseconds where we started, plus this number here, which is about 1/20th of the time constant. It'll switch very fast. In fact, let's go take a look at that on page 21. Here we see this jumping up of the current, and then it passes through 0 very quickly at, in this case, 2.0175 milliseconds. It'll go very close to what we had hand calculated. And this exponential would just keep on going to a minus 542.9 milliamps. Now again, it never gets there, but the equation doesn't know that. So let's go back to page 23. In our Chapter 3 switching circuit, the diode stopped conducting when the voltage across the diode dropped from 0.74 volts to 0.63 volts. When this was occurring, the current was dropping from 27.61 milliamps to just about 0. And this took about 724 microseconds, which is about 2 time constants. The time constant in this problem we just did and the one in Chapter 3 are the same, but the switching times you can see are quite different. Here it was 724 microseconds and now it's 17.56 microseconds. Reason for this is that this time that we're looking at is the time it takes to go from one value to a shutoff point. In this particular case here, we're starting out at a plus 28.52 milliamps, and we're trying to shoot to a minus 542.9 milliamps. The time it takes to cross 0 is quite short. These two devices switch at the same speed, but they're shooting for 2 different values. And that's why this circuit that we just looked at is much faster than when we did in Chapter 3 using a damping diode. And this is supplemental problem 412.